So I'm the chair of this afternoon session, and so our first talk is a plenary talk, and it's my great pleasure to introduce Professor Zuowei Shen, and Professor Shen is the Vice Provost and the Distinguished Professor of the National University of Singapore, or NUS. He is a renowned mathematician and is well known for his fundamental contributions in mathematical foundations of data science, especially in approximation theory, wavelets, image processing, computer sensing, computer vision, and most recently, machine learning. He sits on several editorial boards of top journals and has been invited to speak at many international conferences and congresses, which includes the ICM and also the ICIM. And Professor Shen has received numerous awards and honors, including the NUS Outstanding University Research Award and the Wavelet Pioneer Award given by SPIE and the National Science Award of Singapore, and has been elected as Fellow of SIAM and AMS and the inaugural Fellow of the Singapore National Academy of Science. So without further ado, let's welcome Professor Shen to give this is the second plenary talk. Okay, Professor Shen, please go ahead.
Thank you. Thank the organizers for the invitation, and also thank Lindong's introduction. Today, I'm going to talk about the approximation theory about deep neural network. I will start with the brief introduction of the approximation theory and connect it to the deep learning. And the key difference between the classical approximation theory and approximation theory of deep learning, deep neural network, is the classical approximation theory essentially based on the projection or semi-projection, and the deep neural network approximation is based on approximation of the compositions of functions. And so the second part of my talk will about the approximation through the compositions. And the third part of my talk is go to the fully collected networks especially generated by the ReLU, and how we estimate the approximation rate in terms of the number of neurons. And finally, I'm going to talk about this universal approximation property. And this is a special kind of, we design a special kind of a neural network, which is the hypothesis generated by the finite number of neurons, which can be dense in say continuous function space, and in fact in ALP space. So let's start about this brief approximation theory. Okay, let me see how can this. Okay, for a given target function f and an error bound epsilon, the approximation is to find a simple function g such that g can approximate f, but g is much simpler. And sometimes f can be from Rd to R, and g can be from Rn to R. So g can be, you can choose as simple as possible, like g being a linear function. To make this approximation have any sense, and we needed to have a map T. T maps from Rd to Rn such that G composed with T have a good approximation of F. So in the classical approximation theory, this is either linear approximation. Linear approximation, as I said, is essentially either a projection or semi-projection. And also, more recently, about the SN term approximation, which is non-linear, but for example, wavelets, the base of the wavelet theory is N-term approximation. We're gonna by the sparsity, and that's why wavelets are very useful for the imaging, because imaging is sparse in the wavelet domain. Okay, so also classical learning theory, basically you already parameterize the map T, but with so that your T can be learned from the data. Or the classical approximation, classical learning theory, the T only parameter by a fairly few parameter. It's normally like the one hidden layer kind of the neural network. The deep neural network, you completely parameterize the T. But T, you basically further decompose to the compositions of many layers of T, and each layer of a map is simple, and each layer of a map are parameterized, and you can approximate them. Okay. Well, okay. This let's the neural network denoted by phi x theta. Theta is a parameter, and x is your domain variable. So the neural network you can written as G composed with T is the same setting as we have. Then the T, the map, will further become a compositions of many layers of T1 up to TL. Okay, each TI can consider as one layer of the neural network, and G is your outlet layer, outcome layer. So each TI you can parameterize is a composition of the two functions. One is the affine map, W affine map. W is a linear map, and this is the affine map. Then compose with a sigma. Sigma is the activating function, and so each layer is again the composition of the two maps. One is the linear map, one is by the activating. So this linear map is a factor, so activating is operated on each component. So how do we parameterize this TJ? Each TJ, your WJ is the metric, is all the parameter to learn, and your BJ. So there are a huge number of the parameters, that's W0 up to WJ. This is your parameter to learn. So this is the normal neural network if we written in the mathematical form. So what's the approximation of a deep learning? So you want to estimate the errors. So fix the data, you want to estimate this error is for you. Okay, error is a distance function. Okay, your distance, this is the f is the target function. This is the you fix data, you have phi x data. This is the function in your hypothesis space. So this is the distance, and this is the distance take the expectation of x on the distribution. Okay. So for the simple case, let's say your error to be the Euclid norm, Euclid distance, and U to be a uniform norm distribution. The omega you take a simple is a unit cube. Then your RD is the base cases. This is essentially say is the L2 norm, L2 distance between your hypothesis space generated by your neural network to the target function. Okay. Theoretically, you want to find what? All the learning, theoretical learning is basically you find the theta D. Okay. We make this cost function to be minimal. Okay. Realistically, practically, you don't have a F. So you only have a F, so you cannot learn zeta D. Okay, you may not know the distribution. So instead you find a minimization of a minimizer of this, you're doing the empirical kind of risk function. Because you only have a data, and instead of using RD, you're using the empirical risk LHD data. Okay, this is a discrete kind of errors. So deep learning, supervised learning, especially supervised learning, is to find minimizer of this RSD data. Okay, find data S, so which minimize this cost function. Of course, this is the optimization problem, which is very high dimension and non-convex. So at the end, you will get your numerical solution, whatever numerical algorithm you use, you get a data N. So what we like to know is estimate RD zeta N. That's the arrow you want. Okay, once you have a data in, you can get a function from hypothesis space, and you want to know this distance. That's what you want to know. But this distance is that you can be bounded by 3 terms. First term is RD at delta D. That's either your distance from your hypothesis space to target function. Okay. This second is optimization error because you're doing your numerical solution to the minimizer of your empirical model. And the third one is we call generalization error, that basically between your best model and your empirical model. That's the distance. Okay. So if you really want to know the errors of your deep neural network results, you have to estimate these 3 errors. And for this talk, we are going to focus on this approximation error. We call that's the error between your hypothesis space and your target function. And among these 3 errors, approximation error, independent of your algorithm, independent of your data, it only depends on your architecture of your neural net and your target function space. Okay, all the other error like optimization error and generalization error depends on your data, depends on your algorithm. Okay, so but this approximation error is important because if you don't know this approximation error, even you know this, you have a good estimate for your optimization error or generalization error, you only can know when your target function is in the hypothesis space, how they go down. Okay, but most of the time your target function is not in your hypothesis space. You need this approximation error to bound your real errors. Okay. So to summarize what I have said, approximation error, this is the hypothesis space. Basically giving if you give a network, say a fully connected neural network, you given a depth and a width, then you have a hypothesis space generated by this neural network. Okay, so the approximation error essentially is the distance. You minimize the distance between your target function and the hypothesis space. And practically, you always have a numerical algorithm to get learning the model. Okay, this model is first you have to consider from the generator, but this normally algorithm generated by some optimization algorithm for the imperial risk. So you have this optimization error, and also this empirical risk and the base model also have a distance, this generalization error. Okay, this talk we are going to focus on estimate the approximation error. Okay. As I said, this the deep neural network approximation is basically about the approximation of the by a composition of function. Let's look at what's the setting. The setting is given data, and the key of the supervised learning is to find a map T and G such that G compose T can be used to approximate F robustly. Okay, so so we can start from the mathematical problem and be away. Okay, even independent of the neural network. What is the mathematics behind this? First question you can ask is, well, given a function f and given a function g, because you can choose, as I said, you can choose the linear. Okay, then is there any measurable function, measurable map t from Rd to Rm such that f can be equal to g composed with t? Okay, here is the result. The result says you can do that. Okay, if given f from Rd to R and g from Rn to R, assume that the range of the g is a superset of range of f. Then and the g is continuous. Okay, then you always can have a measurable map such that the f equal to g composed with t. Okay, look at the first condition is clearly you need that. If your g is constant, no matter what you do, you cannot using g to approximate f. And so F so this condition is needed. And say if G is equal to F, your map T is trivial. All right, it is a identity. But of course, you don't know F G that you choose. Okay. And the continuous of G can be further weak, but I don't go to detail for here. So this is the mathematical answer for this question. But this problem is the proof is not constructive. So there exists a T, but how do we construct T? So you want to construct T, we have to relax a little bit. Say if given an error bound epsilon, and can we construct a measurable map T such that the G F composed with G composed with T can have a approximate F as close as you want to. This answer also is clear. Okay, same condition, you need that, then you can kind of have that. Okay, this is in fact you have given F, I can write the T, given F and G, I can write T directly. This is essentially a simple function called the approximation. Okay. So the further question is, can you make T to be a composition of the more simple map? So T become a composition of each Ti is simple in the sense that close to the identity or perturbation of the identity, so that we can learn it. So we can learn have an algorithm to that. Yes, we can do that. Okay, with this, with we can have a T further decompose to the composition and such that, and also we have an algorithm to find the Ti. Okay, this is a mathematical question. Whether our neural network also doing the same thing as that. For the let's look at one example is this residual network. Okay, residual network. The basically the xk it can written in that, and your h is say for the simple case is a ReLU function, and you can do take about that. Then it's a continuous time idealization. You can make this ODE type things, and your control family is F. F is basically all this H. Okay. Well, this residual net can generalize to this continuous time idealization is not our invention. Okay, I think Weinan and Chen Xiao they have done that for this optimization this stochastic gradient descent method. They already done that. Okay, but what our contribution is using this set to consider the approximation. Okay, what's the okay? You can look at that. In fact, this equation you can see you can look at the flow map. Or the flow map you can if your x0 is x, your tx is the end point xt. Then your this flow map itself is our map t essentially. Okay, if you take this way, then you solve it pretty easy. You got this is your flow map. You can see that if you participate your time 0 to tau for the small interval, you get a tau t1 up to t. Okay, you can buy that. Then if your fairly refined participation, your each TJ in fact is close to identity. Okay, if you put this setting, then our is immediately connect to our previous result. That's your basically you have a T as a flow map. You got T kind of decomposition as a sequence of the small simple map, and each map can be kind of close to the identity. And the question is now, given what kind of condition you need to put on the control family, that's basically your activating function, so that your kind of guarantee the G composed with T can have a density. That is the universal approximation property. Result is very simple. Okay, for the actually K is a compact set, and assume that this G also this is the same condition. Okay, this is the image of G cover image of F. That's the same condition as before, and F satisfy some mild condition. I'm not going to give you detail what kind of conditions F needed to satisfy, but I say it's mild because all the example we are considered the activating function we people normally use satisfies this condition. Then for any p, any epsilon, this flow map have this property. Okay, so you do have this universal approximation. If you this is the continuous form. If you if you discretize it, and you can get the exactly property for the residual network. Okay. So this theorem implies that this residual network have a universal approximation property. Okay. So why I said is if the mild condition says if the activating function you are used, for example, is a ReLU or is a sigma, also tau function, then we in the paper we prove that all the fully connected network, ReLU network, satisfy my condition, and also other activating function also satisfy the condition. Okay, and furthermore, even because for the residual net, people normally don't upgrade each layer, so you have a block-wise structure. For using the block-wise structure using the such activating function, they also satisfy condition. So that means all those all the residual nets generated by either ReLU or sigma and tau function, or either block structure or not, they all have a satisfy my condition, and the residual nets do have a UAP, okay, universal approximation property. Okay, this next let's we go to the more technical part of our theory. That is okay. By the way, this piece work is done with this Chen and Linting. Linting is from Peking University. Chen is my colleague in US. And next, I'm talking about the approximation rate in terms of the width and the depth, and for the fully connected, especially for ReLU. And this work basically done with this Zhang Sijing, my student, and now in the Duke, and Yang Haizao, now in the Maryland. Okay, so okay, for given this width parameter n and the depth parameter, that's all you can consider. Okay, for simplicity, just kind of this width n, depth is L. Okay, what we want to ask is what is the approximation rate in terms of n and L for the ReLU fully connected network? Okay, that's the question. So this the first result we had is that for f, say f is a Lipschitz and with a Lipschitz function, then you have this one. Okay, you have this this is what it is. Okay, and where is find the ReLU network? Okay, this is basically exactly what the how depth, how width that is. Okay, of course. Okay, this rate some people may not like it because you have a d here. Yeah, 1 over d here, 1 over d, that means the curse for dimensionality. But you like it or not, if you use the ReLU network, you have a width with n and a depth with L. That's the optimal approximation you can get. That means this is bound almost the same as the lower bound. Okay, you cannot improve no matter what you do. Of course, this is for the Lipschitz function. Of course, you can generalize to the continuous function property. Okay, continuous function, your Lipschitz property, you have to use this module of continuity. Then you can characterize this approximation in terms of the module of continuity. Okay, for the Lipschitz module continuity is simple, but for okay, that's what it is. Okay, this rate is optimal. Okay. So what's in the literature we have? In the literature, we know that when L is 1, that means you have a one hidden layer. Your L is 1, only have a one hidden layer. It is known for the univariate case. In d equal to 1, that's the rate is all is this. Okay, this is well known. Okay, this is well known even in the before deep neural network become hot. It's a classical result for approximation theory. However, for d bigger than 1, everybody says it's true. But for D bigger than 1, for even L equal 1, whether this is true, you have no proof. You ask anybody in the approximation series, they will say it's true, but there is no proof. Okay, I cannot find the proof. There are some proof recently, but they're all adding some other conditions. Okay, what the Yursky do? Okay, our paper also written in 2018. What Yursky do is that what he did is that instead of arbitrary n and l, he said my n is fixed, my width is fixed, the 2D plus 10. Okay, then he has essentially is asymptotic result. Okay, this that means l sufficiently large, your asymptotically has C rate. That's okay. There are many other people also work on this direction. More or less, they put n and l have some relation. That means otherwise, if n and l the two variable, they change the two variable problem to the one problem, put some relations. That means you give a very restrict for your architecture of a neural network. Your neural network, your L and N should have some relation. And secondly, they are asymptotic in the sense they say, okay, my L is sufficiently large. But our results here, we given N and L. N and L has no relation. Okay, you don't need to N L satisfy some certain relation and a certain formula, whatever. But for N and L, we have estimate in terms N and L. It's not asymptotic. Okay, so this all the difficulty we have. That's because it's not asymptotic. All the technical you need is how to do that without asymptotic analysis. Why it's difficult? Because like if I ask you to build a house, I give you an infinite budget. It's easy to do. If I give you a fixed budget to do the things, then you're much harder, right? That's the same thing. If you don't do the asymptotic analysis, basically you fix N and L, you want to have the estimate. Okay. Okay, in fact our first paper is only for L equal to 1 or 2 or 2 and 3. We get that result, and later we get to this is optimal result. Okay, this is a serious paper, and we written on this direction. So as I said, our estimate here is optimal. Okay, that means you cannot improve. And then people are not happy, as I said, it's because of curse of dimensionality. You have a D here. If you still want to use in ReLU, you want to do that unless you do something else, you cannot change things. Okay, so what we do is that first of all we look at this many more problem. In fact your data or what you want to learn this. The function, underlying function is defined in the neighborhood of a small neighborhood of a lower dimension manifold. Okay, your function is defined on the small neighborhood. Okay, people always say my data is in the lower dimension manifold. That's not quite true. I think most of the time in the practice, in the application, your data in the small neighborhood of the lower dimension manifold. Okay, neighborhood is still in a higher dimension. Okay. So if that is the case, and then your DM is a manifold of your dimension of your manifold. In that case, DM is normally much smaller than D, and we can replace this rate that from the D to D delta. D delta is DM log D. So that means that this D delta can be much smaller than D. Okay. That's the result you can get. Okay, this result is already in our very first paper. We already know that if you restrict your you think your function only defined close to a lower dimensional manifold, that's the result you can have. Next, we're talking about the unstable, because this one is our estimate in terms of the number of neurons. Number of parameters, basically. Okay, you have N as your width and L as your depth. Then your number of parameters N square L. That's the estimate in terms of the parameters in terms of N square L parameter. But from our theoretical analysis, in fact, you look at some of the, in fact, even your practical neural network, your final result. You look carefully, your neural network, in fact, has 3 components. The first component we call fire in, and fire in essentially is organize your domain. It's almost independent of your function, target function. It's organize your domain. Then by theta, that's related to your function, related to your target function, related to your data. Basically, the ability for your neural net to represent those data. Okay. Then the third part is fire out. Fire out is once your data is being well represented. Well represented means represented close enough. The rest is just fire out is kind of approximate the interpolation of the data. Once you have an interpolation in one composition, you get a good approximation for everybody. So you at least in our theoretical analysis, also you look at some of the practical neural network people final result. The fire in, they have 3 components. You can see fire in part is independent of the target function, and fire out part also independent of target function. So you only need to learn fire theta part. That's a representation of your data. Okay, so this is fire in. How do we get fire in, fire out? From our theory, we know clear, but for practical, you can maybe from learning from other data or whatever. Okay, so now your parameter wise is much less. So basically, fire out, fire in can be fixed, and you just need to train fire theta. If your fire theta have an n parameter, then we have a result. Our result is, in this case, your result is much better. Your for this, if you're using intrinsic parameter, you can have this approximation. Okay, your phi is your best function to in your hypothesis space to approximate target function. That is 2 to the minus power n. Okay, that's a much better result. So no curse for dimensionality for this result. Okay, and of course your other words, the Lipschitz, you kind of become a continuous function. You can have the same result is replaced by module of continuity. And also here we say LP. You kind of change it to the L infinity norm by adding few parameters. Okay, just ON parameter. We can get the results for this. Okay, this is our recent paper just accepted by the ICML. Okay, so another way that if you still love the ReLU, what we do is that we do something different. Okay, now all the neural network is about your architecture. You have 2 important parameters. One is the depth. One is the width. Okay, these 2 variables very important for the architecture. Is a basic architecture the index. Now introduce beyond the depth and the width, we introduce the height. Okay, what's the height? Essentially, for your given network, you look at all the activating functions as ReLU. I replace the ReLU by a small ReLU net. That's you form a height. Okay, you define that recursively, and you get we call the nest net. Okay. Well, each one is bigger than the next one. Essentially, you look your S height S, your each neural is activating function is replaced by the lower the nest net. Okay, so your high S is your each activating function replaced by this one. Okay, this is the basically you have a network, you replace activating function by small net. Okay, this is high 2. Okay, high 1 is just ReLU network. Okay, if you have with this, we have the following result. Your height, okay, same. For your the parameter. Okay, your network, you have this number of the parameter. Okay, C is dependent on what kind of norm you guess. That's the C. Then this number of parameter. The key here, your height is on the component. Okay, if you have a height up to the D, then you cancel the this D. Okay, so this is what it is. Okay, this is also another way. If you want to improve approximation, using the heights is the new architecture. This is our also recent paper. Okay. So for the ReLU, if we want to do ReLU, we have many. If you want to classical ReLU network fully connect, your approximation is what we get is optimal. So you want to improve. That's the a few options you can have. Other option you can do is, of course, you still want to do ReLU, you don't want to do all this fancy stuff. You say, okay, then you reduce your space. Okay, you make a smaller space, or because the continuous space may be too large. LP space is too large. You can make a smaller space. You can get the result. Okay, the smaller space like a how small it is. Okay, for example, you reduce the space to the polynomial space. Okay, that's the very small space, but it's very important space. Okay, for all the polynomial space, then you have a result. You have a polynomial space. You have any polynomial of degree k. You can have this kind of if you have a net have n and k as n and l as your the width and the depth. You basically have this. Okay, your L is on the power. Okay, so this also you don't have a D. Okay, polynomial. Okay, for polynomial, you have degree k is here. This is very good. If you know anything, if you know anything about a classical approximation, all the classical approximation, essentially, what do people do? All the classical approximation, people first do reproduce some polynomial. Okay, you have to locally reproduce the polynomial. Then using Taylor expansion, you can get a order of the approximation. Okay, that's all the no matter what you do, you find the elements wherever it's, or you do even do the spline. Or fundamental idea is that now your ReLU cannot reproduce polynomial because you only can reduce polynomial of degree 1. Okay, you cannot reproduce high degree polynomial. However, ReLU can approximate high order polynomial in a very fast way. If you using the sufficient large layer of depth, it's very fast. Okay, so that means you can have a hope for the smooth function. You can have a better approximation. That's true. That's our result. This is the result. Okay, if you have a function smooth S, then you also have a component here, S here. Okay, so this so the smooth function you can have a much better approximation. That's the same as the classical approximation. Okay, you have a smooth, you have a here. Okay, but we don't have a reproducing polynomial, but we have a actually close approximation of the polynomial. Okay. Other choice you may kind of have is that you give up a ReLU, or you don't fully. If you don't want to fully give up the ReLU, you give up some part of ReLU. So you instead of ReLU, only using ReLU in your network as an activating function, you can have a two choice. You can have floor and ReLU. Okay. If you have these two choice, you are using floor function and ReLU function as your activating function. That's in fact it's the same neural network. Essentially, the activating function you can have freedom to choose. Okay. In fact, you don't need to use too many floor. Only very few places you need a floor. If you have that, then you can have a good approximation. The approximation. Okay, let's look at this continuous function like the Hulu function. Hulu function you have this d at the n to the power square root of L. Okay, this is also very good. Okay, this is no curse of dimensionality, nothing. Okay, but you have to use floor function in your network. Okay, people may not like it, but this is what it is. Okay, you can give up a floor function. You can choose some other function. We have a result at either 3 hidden layer. You can get a good approximation. Okay, so this is if you want to. Okay, now you have many choices. Okay, you either you want to go beyond ReLU, you have that. Okay, you have this one. Okay, this one people don't like is that one thing is you do using floor, which many people. In fact, floor is not bad. Okay, yeah, ReLU is a piecewise linear spline. floor function is essentially piecewise constant. Okay. Then we talk about the next. If we next we are going to do a very, I think, a very surprising result. Okay, we find a simple activating function, replace the ReLU. Once you do that, you have what? You have an approximation for fixed number of neuron, for arbitrary close of approximation. That's the surprise. Okay, what's the simple function we use? The simple function is a function also not hard to computing. In fact, okay, this is the function you use. This is our new activating function. This activating functions is essentially, okay, from minus infinity to 0, you are using we call this soft sine function. Okay, this is soft sine function. Okay, this is essentially like a sine function. Okay, you smoothize the sine function basically. Then from 0 to positive infinity, you have this hat function. This combination with the ReLU, but it's periodic and with the period 2. Okay, this is your activating function you use. Okay, if we're using this activating function, what kind of result we can have? Result is amazing. Okay, let's because okay, I think I should define the hypothesis space at the beginning, but let me first define. Okay, you have this magic activating function sigma, and because the region net is same. Okay, the neural net is same. You have a G composed with a T become a T1 to TL, and each T you have a 2 composition. It's one is affine, one is affine and composed with your activating function. Now instead of using ReLU, you're using ours is the magic activating function. Okay, so you have this is your space, and this is your hypothesis space. Okay, for any given width and n and corresponding hypothesis space can be defined as this one. That's what I should define at the beginning. But anyway, this is the parameter. Okay, theta. This is your hypothesis space. But our theorem is the amazing part of our theorem is the hypothesis space HD. Okay, for given L and Ln is dense in the continuous function space. Okay, whenever your n just needs this number, n connect with the D. Okay, your L just need to bigger than 11. Okay, so that means you have any L bigger than 11, you have any n bigger than this number. So this is the final number. Any number you choose as long as bigger than the 2 magic numbers, this, your hypothesis space will be dense in that. Okay, you look at other universal approximation property people talk about. People always talk about, like even for the ReLU we do it. We have an n and L. You give an n, you have an L bound, and you want to L bound L to go to 0. You need n and L go to infinity. But here you don't need it. Your L and n just need to be a final number. Your hypothesis space already dense in that. That means, okay, implies the universal approximation property for fixed width and depth. Okay, any number bigger than 2 magic number. And that means for aperture f and epsilon, there exists a phi such that this is smaller than. Okay. This property this is not only for continuous function. This is true for any f in LP space, and your distance for LP norm will be smaller than arbitrary epsilon. Okay, so if you still think about the approximation rate, then your rate is infinity, right? In terms of n and L, you fix the n L, your rate is infinity. So this is a very much surprise result to me. Okay. Okay. If you don't like this function, this what's the function? If you don't like this periodic kind of function, we can have because some people like sigma type of function. We can make, once you have a sigma, you can generate, in fact, in our paper, you can see, you can generate infinite many function have this property. This is one of them. This is the shape more or less like a sigma function, but it's not a sigma function. It's a, then for this function, the hypothesis space, as long your n is L is bigger than 66, your n is bigger than that, your this hypothesis space will still dense in C and dense in LP, any P. Okay, P is smaller than infinity. Okay, what's this sigma? This sigma is okay. Essentially, more or less, okay, when X form is still is like that, and the change is only minus infinity to 0 is same as before, and 0 to infinity you change. Okay, you change. That's what it is. Okay, you have this function. Okay, that's what it is. So this function you also have a this. Okay, I think next we look at this setting. You look at this classification problem. Okay, if you have this binary classification, and you can say, okay, binary classification, you can it's essentially you approximate a function f. Okay, the function itself is very simple. Your function itself is you have a two domain in a very high dimension. Omega 0 is 0, and binary is the cat and the dog. At omega 0, the domain equals is a cat, and another region is a dog. Okay, this is the binary classification. So most of the time, the function for the neural network to approximate is the function itself is very simple. You think about it, it's a 0 and 1, it's a two domain, but the domain is very complex. Okay, that's why you see the omega 0, omega 1 is so complex. It's in a very high dimension, and the geometry is very complicated. In this the omega 0, omega 1 is a very high dimension kind of manifold. It's very complex, complicated manifold. Okay, that's but look at the function itself is very simple. Then our theory kind of our system we can show that this function in fact is in your hypothesis space. Okay, for n bigger than that and L bigger than 2 or 12. Okay, so for any using our systematic activating function for any, as long as n bigger than L bigger than that, your class this function you want to approximate is in your hypothesis space. As long as your omega 0 and omega 1 are bounded and their closure have no intersection. I think this condition is not too strong. If you have a two set, you want to classify with a closure is not have an intersection. I think you don't have a way to separate them. Okay. Under this condition, your f is in there in your hypothesis space. What does that mean? Okay, you go back to our original results, and our original, you think about the arrows for the supervised learning. Your classification is supervised learning. Your supervised learning, you have 3 errors. Okay, now this tells you don't have an approximation error. So your overall effort, you need to what? Reduce the generalization error and optimization error. Okay, that maybe that's also indicates why this deep neural network is very successful in classification, because you don't have approximation error. Okay, so there exists a phi in that. That's mean. This means there is no approximation error as a classifier, and of course this we choose the binary case. We make it simple, but in fact you have any number of classification problem. There's a underlying function f is still in your hypothesis space with the generating activating function we define. Okay, to conclude, the to estimate supervised errors of supervised learning, you need in fact, you need to estimate 3 errors. And in this talk, we focus on the approximation error. Okay, approximation error is you give a neural network the generated hypothesis space. The approximation error is essentially the distance between the hypothesis space to the target function, which can be estimated independent of data, independent of your algorithm. Then you have other 2 errors, which I think is much harder, to me at least, the optimization error and the generalization error, which will be depend on your data, depend on your algorithm, and depend on many. So some people do question, say, oh, why I should go all these 3 things? This is what are the learning, all the learning algorithm go through. Why not I have this neural net? I just found a magic way that sometimes like classical approximations they do. They have a scheme to get an approximator directly. The approximator may not be your best approximation, but it's bounded by some constant times the best approximation bound. Okay, so can you do that? I don't know. Do that, good. You have a good scheme, but so far I don't know. Okay, so this is can discuss what we can think about it, but all the learning algorithm you go through this channel. Okay, so I think I finish my talk here, and thank you, and I'm ready to answer your question.